All right, today we are going to crack a code. Not just any code, but the invisible language that, and I mean this literally, powers our entire modern world. We're talking about electricity. And we're going to figure it out using a pretty unusual key.
I mean, seriously, have you ever stopped to think about it? The phone in your hand, the Wi-Fi in the air, the light in your room. It all just works. But it all runs on a set of principles that are completely invisible. So how are we supposed to even begin to grasp it?
Well, it turns out it's basically a secret language, one that's spoken in volts and amps and these things called magnetic fields. And, like with any language, once you get the hang of the basic grammar, you can start to understand the incredible stories it's telling all around you.
And here's our secret weapon. We've got our hands on an actual electrical circuit theory exam. But wait, don't panic. This is not a test. Think of these questions as our Rosetta Stone. Each question is a clue, pointing us directly to one of the core, must-know ideas of electricity.
Okay, so let's dive in. We have to start at the beginning, right? With the most basic, fundamental forces, these raw pushes and pulls that are just there, all around us, all the time.
So, our first question from the exam. It sounds almost philosophical. It asks about the energy that's stored in a vacuum. A vacuum? I mean, come on, how can you possibly have energy in nothing?
And here is the mind-bending answer. The energy isn't stored in an object. It's stored in the field itself, in the space. This formula basically says the energy, W, is all about the strength of the electric field, E, and a property of that empty space. It's like the space itself has potential, and energy woven right into its very fabric.
And this is not some gentle, abstract concept. Not at all. To make it real, another exam question has us calculate the force between two strong magnets. And the answer is over 63,000 newtons. To put that in perspective, that's more than enough force to lift a car. These invisible fields are no joke. They're incredibly powerful.
Now, that same exact principle scales all the way down. Another question shows that two regular wires, each with just 1 amp of current, still push or pull on each other with this tiny but totally predictable force. And it's that precise, predictable force just scaled up millions and millions of times that makes every electric motor in the world spin.
So we've got these fundamental forces. They're real, they're powerful. The next logical question is, how do we control them? How do we make them do what we want? Well, that's where engineering comes in, by creating components designed specifically to manage that flow.
Our exam guide points us to a really beautiful idea here. Usually we think about circuits in terms of impedance, how much they resist the flow of electricity. But engineers often just flip that concept on its head and use admittance, which is a measure of how easily a circuit allows or even welcomes the current.
And it gets even deeper. A part of that admittance is something called susceptance, and that's the real answer to the exam question. It's a precise number that tells you how willing certain components are to let alternating current flow through them. It's a total shift from thinking about fighting the flow to instead enabling it.
Okay, another question introduces us to a material's magnetic personality through something called a hysteresis loop. The two key ideas here are reeminence, you can think of that as the material's magnetic memory, and coercivity, which is kind of like its magnetic stubbornness, how hard you have to work to erase that memory. These two properties are exactly why things like hard drives and transformers work at all.
And what about just storing energy? Question 16 gives us a real-world problem. How much energy is inside a particular capacitor? The answer is 25 joules. And that right there tells you what these things do. They're basically tiny, super-fast rechargeable batteries, grabbing energy from the circuit and holding onto it until the perfect moment.
All right, let's keep building. We've got the forces, and we've got the components to manage them. But what stops it all from just being chaos? What makes it all predictable? Well, for that, you need rules. And in the world of electricity, the rules are absolute.
So exam question 9 points us to maybe the most important traffic law in all of electronics, Kirchhoff's first law. I know, it sounds super academic, but what it means is actually incredibly simple and really powerful.
The best way to picture it is with water pipes. Imagine a point where a few pipes meet. Whatever amount of water flows in, the exact same amount has to flow out. Simple as that. No current, no water, just vanishes. And that one simple rule is the foundation for figuring out even the most ridiculously complex circuits.
Now check this out. Question 12 looks like it's from the wrong exam entirely. It sounds like a chemistry question about plating silver onto something. But the specific answer, the amount of silver, isn't what's important.
This question is sneakily demonstrating another powerful law of nature.
What we're really seeing is Faraday's law of electrolysis, and what it proves is that electricity isn't just some abstract energy. It's a physical, chemical, creative force. This law gives us a precise recipe that connects an amount of electricity to an amount of physical matter created. It's the basis for everything from coating jewelry to refining metal.
And for our last rule, question 20 asks us about a law that's all about direction. And that brings us to Lenz's law. So, if Kirchhoff's law was about conservation, Lenz's law is all about opposition. You could call it nature's contrarian.
Here's the core idea. Nature loves things to stay the same. It loves equilibrium. So if you try to change a magnetic field near a wire, the wire will instantly create its own current and magnetic field to fight you, to oppose your change. And that fundamental principle of pushback? Well, that's exactly how electrical generators work.
Okay, let's step back for a second. We've used this exam as a key to unlock the forces, the components, and the unbreakable laws. We've basically learned the language of electricity. So, why does any of this matter? Because what we've really done here is piece together the entire blueprint for modern technology. We started with the raw forces of physics, then we saw the components engineers invented to control them, and finally, we saw the elegant laws that make the whole system predictable and reliable.
These aren't just abstract ideas on a test. Every single time you charge your phone, or connect to the internet, or start your car, you are kicking off a complex, high-speed dance involving these exact same principles. This is the living, breathing source code of the 21st century.
So the next time you do something as simple as flip a light switch, just pause for a second. You're not just closing a circuit. You are the conductor of an invisible symphony of forces and flows, all playing in perfect harmony, all following the rules that we just decoded together. Makes you wonder, what other secret languages are out there just waiting for us to find the key?